Section 1.5, 5 equations for motion with a uniform acceleration. In a previous video, I've shown you how to derive 5 equations that are commonly used for kinematics. And Table 1 from your textbook summarizes these 5 equations. It tells you the variables found in each equation and the variables not found in each equation. We're going to practice with 3 sample problems how to use the 5 equations for accelerated motion. Sample problem number 1. A sports car approaches a highway on-ramp at a velocity of 20 meters per second east. If the car accelerates at a rate of 3.2 meters per second squared east for 5 seconds, what is the displacement of the car? Take a look at all the variables given. So we have the velocity of the car as it approaches the on-ramp. This is the initial velocity of the car, and it's 20.0 meters per second east. Next we have the rate at which the car is accelerating, and that's 3.2 meters per second squared east. And the amount of time the car is traveling for, and that's 5 seconds. What they want us to find is the displacement during this 5 seconds. So what we need to do is look at Table 1, find an equation that incorporates everything that's given and required. So V1, A, delta T, and delta D. If we look on the table, that brings us to equation number 3. That equation is delta D is equal to V1 delta T plus 1/2 A delta T squared. Sub in the values from above. Be sure to include the direction. So we have 20.0 meters per second east times an elapsed time of 5.0 seconds plus 1/2. Acceleration is 3.2 meters per second squared east times 5 seconds squared. Be careful when punching this into your calculator. You may have to do it a couple of times to verify that you've done it correctly. If you punch this into your calculator correctly, you will end up with 140 meters east. Therefore, the displacement of the sports car during this 5 seconds is 140 meters east. Sample problem number 2. A sailboat accelerates uniformly from 6 meters per second north to 8 meters per second north at a rate of 0.50 meters per second squared north. What distance did the boat travel? So let's look at what's given in this question. So we have 6 meters per second north, 8 meters per second north, 0.50 meters per second squared north. Let's list these variables with the correct symbol. First, we are given the initial velocity of the sailboat, which is 6 meters per second north. Next, we are given the second velocity, or final velocity, which is 8 meters per second north. And finally, we're given acceleration, which is 0.50 meters per second squared north. And what they want us to find is the distance this object travels. Since the distance is in a straight line, it would be equivalent to finding the displacement. So we have V1, V2, A, and delta D. Take a few seconds and look at Table 1 up above and determine which equation includes all the variables given and other variables required. Note, in this example, delta t is not present, so you'll need to find an equation that does not require delta t. If you look correctly, you'll notice that we're going to use the equation v2 squared is equal to v1 squared plus 2a delta d. This is equation 4. First thing we want to do is rearrange this equation to solve for delta d. So let me correct this. This is plus 2a delta d. So we want to get delta d by itself. The first thing we're going to do is take this v1 and bring it over the equal sign. When we do, it becomes negative. We are left with 2a delta d on the right side. Let's divide both sides by 2a, allowing these to cancel out. We are left with delta d is equal to v2 squared minus v1 squared over 2a. Now we can sub and solve. v2 is 8 meters per second north squared, and v1 is 6 meters per second north squared over 2 times an acceleration of 0.50 meters per second squared north. All of the directions are the same, so we can proceed algebraically. Be sure to square each of these quantities in the numerator before you subtract them. If you do this correctly, you should end up with a displacement of 28 meters north. Let's try sample problem number 3. This is a 2-part question. A dart is thrown at a target that is supported by a wooden backstop. It strikes the backstop with an initial velocity of 35 meters per second east. The dart comes to rest in 0.0050 seconds. Part A. What is the acceleration of the dart? Let's start by writing down what's given. They tell us the initial velocity. They state this explicitly, 35 meters per second east. Tell you the amount of time is 0.0050 seconds, and they want us to find the acceleration. There's another piece of information that is implied. Again, this is a bit of a trick. I'm not sure if this is the first time we've seen it. Definitely won't be the last. They tell you that the dart comes to rest. Whenever you see this, you know that the final velocity of the dart is 0. Whenever an object comes to rest, its velocity will come to 0. So now we need to look for an equation that incorporates everything that's given and everything that's required. So the equation that we will use is equation number 2, which states v2 is equal to v1 plus a delta t. This is actually just the equation for acceleration rearranged. So we can rearrange this equation. Firstly, bringing the v1 over, changing this to v2 minus v1 equals a delta t. Then divide both sides by delta t. So we have acceleration is equal to v2 minus v1 all over delta t. Let's sub and solve. Make sure you put v2 and v1 in the correct order, or you will get the wrong direction. So that's 0 minus 35 meters per second east divided by 0.0050 seconds. Punch this in your calculator to determine the acceleration. What you end up with, to two significant digits, is negative 7.0 times 10 to the power of 3 meters per second squared east. That's 7,000, negative 7,000 meters per second squared east. Another way to write this is positive 7.0 times 10 to the power of 3 meters per second squared west. If you change the sign, you change the direction. Negative accelerations imply that the object is coming to rest or slowing down. In part B, they want us to determine how far the dart penetrates into the backstop. So we can use all of the variables we were given and all of the variables that we found. So we have V1, 35 meters per second east. V2 we said was 0. Delta T is 0.0050. And the acceleration we just determined was negative 7.0 times 10 to the power of 3 meters per second squared east. And we want to find delta D. If you look at table 1, you'll see that we have every possible variable for all of the equations that are above. So there are many equations that we can use. You can choose which one you feel would be the easiest. For example, you can choose delta D is equal to V1 plus V2 over 2 times delta T, or you could use equation 3. Delta D equals V1 delta T plus 1/2 A delta T squared, or equation 4, and again equation 5. Let's use equation number 1. We'll sub and solve 35 meters per second east plus 0 divided by 2 times 0.0050 seconds. If you punch this into your calculator, you should end up with 0.088 meters east. That is correct to two significant digits. Please try the practice problems in your homework. Be sure to use the solutions found online or at the front of the room in a binder to help you along.